Assalamualaikum and salam sejahtera to all. Today we delve into an essential chapter that focuses on a crucial aspect of particulate matter control. We are already in chapter 55, Filter and Baghouse. I'm thrilled to have you join me as we explore the basic things of filtration and baghouse systems, which play a vital role in maintaining clean and breathable air in various industries. In our previous lectures, we discussed the different types of particulate matter control systems, including settling gravity chambers or gravity settlers, cyclone separators, and electrostatic precipitators, in which each are designed to mitigate specific particulate matter emissions. This time, we shift our focus to an incredibly effective and widely used method for particulate matter control, which is a filtration system, specifically filter and baghouse technologies. These systems excel at capturing and removing particulate matter from gas streams, which is very effective in removing particulates over the size range of 0.1 until 1000 micrometers. It offers significant advantages in terms of efficiency, versatility, and cost effectiveness. Throughout this lecture, we will unravel the inner workings of filter and baghouse systems, examining their component, operation principles, and applications across a spectrum of industries. We will also discuss on the cost estimations involved in this type of air pollution control system. Filtration is the separation process of removing solid particles, microorganisms, or droplets from a liquid or a gas by depositing them on a filter medium, also called a spectrum, which is essentially permeable to only the fluid phase of the mixture being separated. The particles are deposited either at the outer space of the filter medium and or within its depth. The permeation of the fluid phase through the filter medium is connected to a pressure gradient. The liquid more or less thoroughly separated from the solids is called the filtrate. Effluent, permeate, or in case of water treatment, clean water. As in other separation processes, the separation of phases is never complete. Liquid adheres to the separated solids, which is caked with residual moisture, and the filtrate often contains some solid, which is solids content in the filtrate or turbidity. Multiple mechanisms are responsible for particle capture within dust layers and fabrics. They are initial impactions, Brownian diffusion, interception, and electrostatic attraction. Particles are collected on a filter by a combination of several mechanisms. The most important here are impaction, direct interception, and diffusion, which account for 99% of collection of particles less than 1 microns. Impaction is an inertial mechanism that is most effective on particles larger than about 1 micron. In collection by impaction, the particles in the gas stream have too much inertia to follow. These too much inertia to follow the gas stream lines around the fiber and are impacted on the fiber surface. It is effective in fabric filters because there are many sharp changes in flow direction as the gas stream moves around the various particles and fibers. Unlike some types of particulate collection devices, there are multiple opportunities for particle impaction due to the numbers of individual dust-caked particles and fabric fibers in the gas stream path. In the case of direct interception, the particles have less inertia and barely follow the gas stream lines around the fiber. If the distance between the center of the particles and the outside of the fiber is less than the particle radius, the particle will graze or hit the fiber and be intercepted. The third collection mechanism is that of diffusion. In diffusion, small particles are affected by collision on a molecular level. Particles less than 0.1 microns aerodynamic diameter have individual or random motion. The particles do not necessarily follow the streamlines but move randomly throughout the fluid. This is known as Brownian motion. Particles may have a different velocity than the fluid at some point, could come in contact with the fiber and be collected. Other collection mechanisms such as gravitational settling, agglomeration, and electrostatic attraction may also contribute slightly to particle collection in filter and baghouse. Large particles may be overcome by the force of gravity and settle in the hopper. Particles can agglomerate or grow in size and then be more easily collected by the fibers. Some particles have a small electrostatic charge and can be attracted to a material of opposite charge. Electrostatic charges could, on the other hand, have a bad effect if the charges of the particles and fiber are the same. Electrostatic charges can be particularly useful for the capture of particles in the submicron range. The use of a selected fiber material or a specially coated material may enhance particle capture. Particles are also collected by gravitational settling. Relatively large particles are overcome by the force of gravity and fall into the baghouse hopper. This force is particularly important when dust-laden gas enters the baghouse through a hopper inlet. In general, filter and baghouse consists of three important parts, which are filter bag, cleaning mechanisms, and collection hopper. Other components that should be considered are filter medium and support, filter cleaning device, shell, and fan. Now, let's look at the filter and baghouse components.
There are many different sizes and designs, but baghouses all operate in the same basic way. 1. The dust-laden or particle-laden air or gas stream enters the baghouse, travels along the surfaces of multiple fabric tubes, and then passes outward or inward through the fabric. 2. The larger particles fall down into a hopper, while the smaller particles accumulate on the fabric surfaces. 3. A cleaning mechanism occasionally removes the particles from the fabric tubes, and they fall down into the hopper from which they are discharged. 4. The clean air or gas stream exits from the top of the baghouse.